11.4 deals with a special type of probability problem. And the reason that we want to look at this type of probability problem is because there will be a shortcut we can use if we have it. And a lot of problems can be boiled down to this type of probability, and it's called binomial probability. Prefix bi meaning 2. And so the overriding thing that makes a binomial probability binomial is just that there are two possible outcomes. Somebody trying to call us here? What's going on? We lost Metro. Doggone it. There are two possible outcomes on each trial. So what that means is, if you take flipping a coin as your experiment, well, if you flip a coin, you're either going to get a head or a tail. So that's two possible outcomes. But other experiments can be considered binomial even though you wouldn't think they would. For example, if I roll a die, you might be thinking to yourself, well, there's 6 possible outcomes if I roll a die. That's true, but if I say, I'm going to roll a 5, I'm interested in rolling a 5. Well, then I can either get a 5 or I can not get a 5. I can get something else. So we boiled it down to 2 possible outcomes. So the 2 possible outcomes we usually call success and failure. Rolling a die, you could say, you could call a success rolling an even. You could call an odd a failure. That would be a binomial experiment because, again, you have 2 possible outcomes. Now, there are three other criteria that have to be met to be considered binomial. But this is the one I want us to focus on the most. But I need to mention the others, or I would be a bit remiss. So I'm going to do that, but first I'm going to try to call Metro back, see what's going on there. But here are the 3 other criteria that have to be met. You must have a fixed number of trials. And by that we mean I'm going to roll the die 10 times or 100 times or whatever. I'm going to toss the coin 1,000 times. It's not an indefinite number of trials when you go to perform your experiment. Next, each trial must be independent. Now that's a concept we haven't talked about much. So now it's time to talk about it. You might have seen that word floating around on some of the pages in your book. What does it mean for events to be independent? Well, it means the occurrence of one has no bearing on the probability of the other. For example, if I had an experiment where I was going to roll a die and then toss a coin, 2 parts to the experiment, okay? And let's say I was interested in rolling a 3 on the die and getting ahead when I toss the coin. Well, whether I roll a 3 on the die or not has no bearing on the probability of me getting ahead on the coin. None. So therefore, those 2 events would be independent. Sometimes in some trials, the occurrence of one thing has a probability on whether the next thing happens or not. For example, you could make this argument either way, but let's take a baseball player. Chris or Robert, did either of you play baseball in high school? No. Little League back in the day? Okay. Well, I played baseball in high school, so I'll use me as an example. So sometimes a hitter can get hot, and sometimes he can get ice cold. So you could make the argument that if I step up to the plate in the first inning and maybe I get a base hit, that would increase the probability of me getting hit the next time I come up because I'm feeling good about myself. Maybe I'm confident. Maybe I just see the ball well from that pitcher or whatever. So those two at-bats, you might say, are not independent of one another. What I do in the first one affects the probability of me being successful on the second one. So sometimes events are not independent, but to be a binomial experiment, each trial has to be independent. Okay, and then finally, the last thing that has to happen is the probability of success on each trial must remain constant. It can't change from the beginning of the experiment to the end. If I roll a die 100 times and I'm interested in rolling fives, the probability of rolling a 5 on the 100th row is the same as it was on the 50th row, and that's the same as it was on the first row. It's always 1 out of 6. So those are the 4 things that have to happen to have a binomial experiment. By the way, sometimes binomial experiments are called Bernoulli experiments, and there's some commentary about Bernoulli in your textbook. He was the one who really moved this study forward. James Bernoulli. Okay, so let me give you an example of a binomial experiment, and let's find probability the only way we know how to right now with the tools that we have, and then we'll look at some shortcut for a binomial experiment. So here's our problem, and we'll just call this example. You're not going to find this in your book, it's just ours. Okay. A fair coin is flipped 3 times. Find the probability of exactly 2 heads. So I got my quarter out. I'm going to flip. I'm going to flip. I'm going to flip. I'd like to know what the probability of getting exactly 2 heads out of those 3 flips would be. That's what I'm after. Now, why is this a binomial experiment? Well, number 1, on each trial, there's only 2 possible outcomes. I could either get ahead or not get ahead. Success, failure. That's first and foremost. And for us, that's going to make it binomial almost every time. But if we looked at the other 3 criteria, each trial is independent of one another. So whether I get ahead on the second flip is totally independent of what I get on the first flip. There are a set number of trials, 3 on this problem, and the probability of success remains constant. The probability of getting ahead is always going to be 1/2. So this is a binomial experiment. Now, here's how we would have to figure this probability right now with the tools that we've learned so far in this class. The probability of getting 2 heads, if we go back to the definition of probability like we did earlier in the class, the probability of getting 2 heads equals the number of ways we can get 2 heads over the number of items in the sample space. Okay, so Chris and Robert, since we're down to you two, let's think about the sample space first, and I'd like for you to tell me what are all the things that can happen if I flip 3 coins? What are all the possible results?
Heads, tails, heads.
Now wait a minute. I'm tossing
Tails.
3 coins, not just 2.
Oh. Heads, tails, heads. That's a lot more to list. Heads, heads, heads. Heads, heads, tails. Tails, tails, tails. Head, tail, tails. Tails, head, head. Tails, head, tails.
Let's see, you're missing 1. And I put this one opposite that one, but I really should put this one opposite the last one. It would be opposite this one. The opposite of head, head, tail would be tail, tail, head. Okay. All right, good. You're right. There are 8 things that can happen. Okay. So it's going to be something out of 8. And then I go through and look at that sample space and see how many of those had 2 heads. Head, tail, head had 2 heads. Head, head, tail had 2 heads. Tail, head, head had 2 heads. So the probability of getting 2 heads exactly, if I flip 3 coins, is 3 out of 8. Now, that wasn't too bad on that problem to list out the sample space. But if I changed that problem to say a fair coin is flipped, say, 10 times, then do you see that to list out the sample space would be ridiculous and darn near impossible? Okay, so that method worked good because we had a small number of trials. So let's look at what your book gives us to help us find probabilities with binomial probabilities, anytime you have a binomial experiment. And so what they give us is something called the binomial probability formula. In my statistics class, that book calls this the binomial probability distribution function. So here is what this formula says. And it's not going to make sense at first. We're going to have to talk through it to make it make sense. It says the probability of X successes is equal to a combination of n things taken X at a time times little p to the X times 1 minus p to the n minus X. That's a lot of letters. I guess we better figure out what all the letters represent. So let's talk about the X first. The X represents the number of successes. On our last problem, it would have been 2 because I was interested in finding the probability of getting exactly 2 heads. The N is the number of trials. What would n have been on the last problem? 3, that's right. And the only other thing I have there is little p. Little p is the probability of success on any trial. So on that last problem, little p would have been a half, because your probability of getting ahead on any one of those trials would have been 0.5, because you're flipping a coin. Okay, so let's see how this formula would have worked on that last problem. So, we were looking for the probability of, you guys said, or I said that x was 2, because we were looking for the probability of getting 2 heads. So if we follow the formula, that equals a combination of n things, which we said was 3, because there are 3 trials, x at a time, which we've already established x is 2, times little p, which is a half, because the probability of getting a head on any trial was a half, to the x, which again is 2, times 1 minus p, or 1 minus a half, raised to the n minus x power, which would be to the 3 minus 2 power, which is obviously just going to be 1. Okay, so Katie, can you work on a 3 combination 2? Chris, can you work on a half to the second power? And Robert, can you work on 1 minus a half to the first power? So Katie, when you got your combination, let me know. It is 3, that's right. Chris, have you got a half to the second power yet? 1/4. And Robert, 1 minus a half to the first? A half, good. Now you can do this on your calculator, but it'd be quicker, just do it in your head. 3 is the same thing as 3 over 1. So 3 times 1 times 1 is 3. 1 times 4 is 4 times 2 is 8. And there's the same 3/8 that we got earlier when we listed out the sample space. So it appears that the binomial probability formula works pretty well. Works pretty good. Okay, well, let's practice this on 3 more problems, and they're going to get kind of progressively tougher as we move through these 3 problems. So we're going to look at examples 2, 3, and 4 from your text. Example 2 says, find the probability of obtaining exactly 2 5s in 6 rows of a fair die. Okay, so the probability of what exactly 2 5s? So we're looking for the probability of 2 successes. So let's think about what we have in that problem. 2 successes means that my x is 2. N was my number of trials. We're going to roll the die 6 times. What's little p? It's the probability of getting a 2 on any roll, the probability of success on any trial, which obviously is going to be 1/6. So if we take those values and punch them into the formula that we just had, then we're going to end up with this, a combination of n things, 6 things, x at a time would be 6 things 2 at a time, times little p is 1/6, raised to the x, which is to the second, times 1 minus p, 1 minus a sixth, raised to the n minus x would be the 6 minus 2, which is to the fourth. So according to your text, a combination 6, 2 is 10. And that's wrong. So we need to erase that. I looked in the wrong spot. A combination 6, 2 is actually 15. A sixth to the second power is 1 over 36. If you take 1 minus a sixth, you're going to get 5/6. And if you raise 5/6 to the fourth power, according to your text, you end up with 625 over 1,296. And if you multiply those three together and convert to a decimal, you're going to get approximately 0.201. So if you roll a die 6 times, your probability of getting exactly 2 2s is right at 0.2, and 0.2 is equal to 1/5. So it's right at a 1 out of 5 probability. So really that problem wasn't much different than the last problem. We're just using a die instead of a coin. Now, let's make the next problem a little bit tougher. Let's go to example 3. This problem is on page 610. A couple plans to have 5 children. Are they crazy? Just kidding. Just kidding. Kids are a blessing. Find the probability they will have more than 3 girls. Assume girl and boy babies are equally likely. More than 3. What does more than 3 mean? Okay, Robert, Katie, and Chris. Is 5 more than 3? Answer the obvious question here. Is 5 more than 3?
Yes.
Is 4 more than 3?
Yes.
Is 3 more than 3? No. And neither is 2, 1, or 0. So more than 3 really means 4 or 5. So we're really looking for the probability of 4 or 5 kids here. Which means this is an OR problem. If it's an OR problem, we'll use the OR formula. The OR formula goes like this. The probability of the first, probability of 4, plus the probability of the second, probability of 5, minus the probability of both, 4 and 5, but that last thing, 4 and 5, are disjoint. They're mutually exclusive events because you cannot have both 4 girls and 5 girls at the same time. So the probability of that is 0. So to work this problem, we got to find the probability of 4 and add it to the probability of 5. So we got two separate little problems here. They're both binomial because when you have kids, you can either have a boy or not have a boy. There are two possible outcomes. Actually, it's a girl in this problem, isn't it? You can have a girl or not have a girl. So what we're going to do is we're going to find the probability of 4 and the probability of 5 separately, both using the binomial probability formula. So to find the probability of 4, that equals a combination of n things. Well, I'm having 5 kids, so 5 trials. X at a time, looking for the probability of 4 girls, times little p, well, that'd be a half, because probability of having a girl is a half, raised to the x, which is to the 4th, and then 1 minus p, 1 minus a half, to the 5 minus 4, the n minus x, or to the 1st. So we'll go crunch the numbers there. Now before we do that, you guys tell me what I would write if I substituted into the formula to find the probability of getting 5 girls. A combination of what? Five here and what over here? 5 again, right? All right, what's going in my parenthesis? Yep, probability of success is a half. Raised to what power? Yep, raised to the 5th. Times 1 minus a half, raised to what power? That's right, it is 5 minus 5, so it would be to the 0 power. Now if you remember from your algebra class, anything raised to the 0 power is equal to 1. So this factor back here is just going to simplify to 1. Okay, so Chris, we're going to have you fly solo and you're going to find, well, no, actually we'll put you and Katie together and you'll find the probability of 4. And we'll make Robert fly solo because his should be a little easier here and he can find the probability of 5. So do a little calculator work and I'll be back with you in a moment. So Chris and Katie, are you in agreement with what you guys got for the probability of 4? So Chris and Katie have said 5 over 32 right there. And I agree with that. Okay. Now, actually, it's 1 out of 32, which as a decimal is 0.03125. And by the way, unless they tell you to give your answer as a decimal or a fraction, it doesn't matter which one you give. And if you take 5 out of 32 and add to it 0.03125, you're going to get a decimal that's equal to 0.1875. Boom shakalaka. Okay, so assuming boy-girls are equally likely, you have about a 0.1875 chance of having more than 3 girls, 4 or 5. What's interesting is if you actually look at the data, I think the world, don't quote me on this, but I think it's like 51% nearly of babies that are born are boys. And so obviously the number would be closer to 0.49 for girls. But if you look at the population of the world, it's flipped. It's more like 51% women and 49% men. So obviously,
Yeah, actually, I just saw something on the news, they were talking about that like the other night. There's more women than there are men in the population.
yeah. So evidently we men do dumb things or something, and I don't know what the explanation is, but there you go. Okay, example 4 is going to be a similar problem, but we're going to take a different approach. So let's take a look at it. It's going to be a little bit of work here. So here's what it says. Andrew Crowley, a baseball player, has a well-established career batting average of .300. So if you don't know anything about baseball, that means every time he goes to plate, he's got about a .3 probability of getting a hit. Okay. In a brief series with a rival team, Andrew will bat 10 times. Find the probability he will get more than 2 hits in this series. More than 2. Okay, so I'm going to talk through this one, and then you stop me if I lose you somewhere. So remember the other day I talked about how you can figure a probability directly, or you can kind of come in what I call the back door. So here's what we would have to do to figure this probability, what I've been referring to as directly. More than 2 would mean 3 or 4 or 5 or 6 or 7 or 8 or 9 or 10, because he's going to bat 10 times. So if I figured the probability that way, I would have to do all of those. I'd have to find all those probabilities, 3, 4, 5, 6, 7, 8, 9, and 10. That'd be, 8 different probabilities I'd have to figure, and then I'd have to add them all together. Now there's nothing wrong with that, but that's a lot of work. What if I came at this a different way? What if I found the probability of getting 0, the probability of getting 1, and the probability of getting 2, and then what if I added those together? So that would give me the probability of getting 2 or less. That's what I'd have there. And then if I took 1 minus the probability of 2 or less, then wouldn't that have to leave me with the probability of more than 2? It'd have to leave me with the probability of everything else. And that way I'd only have 3 probabilities to figure instead of 8. So basically what I'm doing here is I'm using the complements rule that we talked about last time. It says the probability of an event is equal to 1 minus the probability of the complement of an event. And the complement of more than 2 is 2 or less. So that's what I'm going to do. I'm going to figure these 3 probabilities, add them together, and then take them from 1. Okay, so the probability of 0 would equal a combination of, he's going to bat 10 times, so my n is 10. Number of successes is 0. Combination of 10 things taken 0 at a time times a little p, which is 0.300 or 0.3, raised to the x or raised to the 0, times 1 minus 0.3 raised to the n minus x, which would be 10 minus 0, or to the 10th? Okay, and according to your book, that turns out to be 0.0282 if you crunch the numbers there. Okay, then the probability of 1 would be a 10 combination 1. So everywhere I put a 0 before, now I'm putting a 1. So that'd be times 0.3 to the first. Times 1 minus 0.3 to the 10 minus 1, or to the 9th. And according to your book, that turns out to be 0.1211. So the probability of getting 2 hits would be a combination of 10 things, 2 at a time, times 0.3 then to the second, times 1 minus 0.3 to the n minus x would be the 10 minus 2, or to the 8th. And if you do some calculator work there, that turns out to be 0.2335. So if we add those 3 decimals together, we end up with 0.3828. So right at about a 38% probability that Andrew is going to get 2 hits, 0 hits, or 1 hit in the series. So what does that mean for his probability of getting more than 2 hits? It would be 1 minus that. So probability of more than 2 is 1 minus 0.3828. And if you crunch the numbers there, you get 0.6172. So sometimes it's easier to use the complements rule to help us figure probabilities than to figure them straight, figure them normal. Okay, the only thing we have left here is an assignment. So we're going to be looking at page 610, 3 through 9, 20 through 23, and 36 through 45.